Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Section 2. Fouling, Scaling, and Concentration Polarization. Let's look at the content of this section. In this section, at first, we will discuss the filtration mechanism for microfiltration and ultrafiltration. Then, fouling, types, factors, forming, and so on will be discussed. For the scaling problem, we discuss the cells that form a scale and how to determine the compounds that have scale potential and scaling analysis. In this section, we also have concentration polarization that is related to the reverse osmosis and the filtration resistances on the membrane surface. Fouling, scaling, minimization methods such as membrane cleaning, cleaning chemicals and factors, and scale control will be discussed, and in the end, an exercise is presented. Filtration mechanisms. If you remember, in the first section, I said membranes divided into two parts. Membrane filtration and membrane desalination. That membrane filtration is including microfiltration and ultrafiltration, and I'm going to explain filtration mechanisms in these membranes. Filtration mechanisms in microfiltration and ultrafiltration include straining, adsorption, and cake formation. These removal mechanisms are depicted in this figure. Straining. The primary mechanism for removing particles from a solution in membrane filtration is straining. Straining, also called sieving, steric exclusion, or size exclusion, is the dominant filtration mechanism in membrane filtration. Nominally, particles much larger than the retention rating of the membrane collect at the surface while water and much smaller particles pass through. When particles are near the pore size rating of the membrane, however, a fraction of the particles will be captured, resulting in particle removal. Partial capture is caused by the variability of pore size dimensions, non-spherical shape of the particles, and other interactions such as electrostatic repulsion. Typically, both particles and membrane surfaces are negatively charged. Electrostatic interactions may prevent the particles from entering the pores even if the physical size would permit passage. Adsorption. NOM, or natural organic matter, adsorbs to membrane surfaces. Thus, these soluble materials may be rejected even though their physical dimensions are orders of magnitude smaller than the membrane retention rating. Adsorption may be an important rejection mechanism during the early stages of filtration with a clean membrane. The adsorption capacity is quickly exhausted. However, adsorption is not an effective mechanism in long-term operation of membrane filters. However, adsorbed material may reduce the size of pores at the membrane surface and improve the ability of the membrane to retain smaller material by straining. Cake formation. During filtration, a clean membrane will quickly accumulate a cake of solids at the surface due to straining. This surface cake acts as a filtration medium, providing another mechanism for rejection. The surface cake is often called dynamic filter since its filtering capability varies with time, growing in thickness during filtration but being partially or wholly removed during backwashing. While this cake can improve membrane filtration performance, it cannot be relied upon since it is removed with every backwash. Most microfiltration membranes have a homogeneous structure, which means that the structure, porosity, and transport properties are relatively constant throughout their depth. Membrane filters are not constructed of woven or fibrous materials. They are cast as a continuous polymeric structure, as we have already discussed in the previous section, with tortuous interacting voids as shown on this figure. The scanning electron microscope or SEM images, which are microscope images of a 0.2 micrometer polyether sulfone microfiltration membrane. A. Cross-section of the entire membrane. B. High magnification of the membrane surface. And C. High magnification of the membrane internal structure. In contrast, ultrafiltration membranes have an asymmetric structure, which means that the morphology varies significantly across the depth of the membrane. The structure of an asymmetric membrane consisting of an active layer and support layer is shown in the right figure. The active and support layers have separate functions. Filtration through an asymmetric membrane is not the same in both directions. Filtration in the wrong direction would cause the voids in the support layer to become clogged and may cause the active layer to separate from the rest of the membrane. To prevent clogging, some commercial asymmetric membranes have active layers on both surfaces of the membrane with a support layer sandwiched between the two active layers. Reasons for membrane performance decline. Due to the concentration of the water constituents taking place at the raw water side of the membrane, the following effects may occur on the membrane surface as well as on components of the membrane elements or the membrane module, which have negative effects on the performance of the membrane installation. These effects include fouling, biofouling, scaling, and concentration polarization. Fouling. The fouling of pressure-driven membranes is generally referred to the accumulation, deposition, and/or adsorption of foulants onto the surface of membrane and/or within the membrane pores, which can cause the basic membrane functions to deteriorate over filtration time, including permeate flow, solute removal efficiency, and pressure drop across the membrane. Membrane fouling is a major obstacle to the widespread use of membrane technology. Fouling also can be exacerbated by high-pressure operation, so a balance must be struck between flux and fouling. Studies have found that fouling can increase rapidly when transmembrane pressure is above 1 bar. Severe fouling may lead to serious damage and necessitate intense chemical cleaning or frequent membrane replacement. This increases the operating cost of a treatment plant. Processes that rely on membranes must be protected from fouling. Membrane fouling is influenced by three major factors: membrane material properties such as hydrophilicity, roughness, and electrical charge, the feed solution characteristics such as the nature and concentration of the foulant, and the operating conditions such as fouling can be exacerbated by high pressure operation. Fouling types. As you can see in this figure, there are three types of fouling in the membrane: biofouling, colloidal fouling, and organic fouling. The shape of scaling has considered to illustrate you the difference in scaling and types of fouling, which is completely different. Biofouling. Biofouling is very closely related to the living microorganisms in the feedwater that attach onto the membrane surface. In general, the attached microorganisms tend to grow rapidly by forming biological film at the expense of nutrients in the feed. Among the microorganisms that have potential to form biofilm on the membrane surface are Mycobacterium, Phylabobacterium, Pseudomonas, Bacillus, and Lactobacillus. In many cases, biofouling not only increases the membrane transport resistance, but also biodegrades the polyamide selective layer through hydrolysis. There are several main steps in the development of biofilm on the reverse osmosis membrane surface. The very first step involves the preconditioning of the membrane surface by the adsorption of macromolecules such as protein, polysaccharides, and smaller molecules. The combined adsorption of these materials create a nutrient-enriched surface that is ideal for bacterial adhesion. Analyzing several case studies concluded that the major negative impacts of the biofilm formed on the reverse osmosis membrane surface are the decline in water productivity and salt removal rate. The degree of flux decline as a function of filtration time caused by biofouling varies depending on the microbiological properties of the feedwater and the physicochemical characteristics of the biofilm. Generally, the flux tends to decline at a fast rate at the early stage of biofilm due to the early attachment and growth of microorganisms. In addition to flux deterioration, previous studies have shown the increase in salt passage in the permeate of reverse osmosis membrane followed with bacterial cells. The reduced salt removal rate is attributed to the biofilm enhanced osmotic pressure phenomenon that hinders the back diffusion of ions, making them concentrated adjacent to the membrane surface. Particulate and colloidal fouling. Particulate fouling occurs when suspended solids and/or colloidal material clog the holes of a membrane or adhere to its surface. As particles accumulate on the membrane, they form a cake layer that obstructs water from flowing through the membrane's pores, resulting in the increased pressure differential measurements and increased energy consumption. Particulate or colloidal fouling is caused by the presence of non-biological and inorganic particles such as silt or clay in feedwater, especially when the stream is sourced from a body of surface water. To measure the relative risk of particulate or colloidal fouling, water treatment specialists typically measure the Silt Density Index or SDI of a feed stream. SDI measurements are especially important when installing reverse osmosis systems, as these have the smallest pores of any membrane filtration systems and are consequently much more vulnerable to particulate fouling. Particulate fouling can typically be prevented by applying appropriate upstream coagulation and filtration. Organic fouling. Organic fouling is the combination of deposition, reactions, and interactions of high molecular weight organic molecules such as natural organic matters with the membrane surface. These organic matters usually consist of humic substances, polysaccharides, proteins, lipids, nucleic acids, amino acids, organic acids, and cell components. For surface water or seawater, natural organic matter is often used, while for wastewater, effluent organic matter is often adopted. In wastewater treatment, organic fouling is a main problem in reverse osmosis treatment because the effluent organic matter concentration between 10 to 20 ppm is much higher compared to typical natural organic matter concentration in surface waters between 2 to 5 ppm. One of the commonly used techniques to perform the autopsy and identify reverse osmosis foulants is electron microscopy. This image compares the scanning electron microscope image of foul reverse osmosis membranes with respect killing surface in two different fouling mechanisms. The left image are membrane surfaces before fouling, and the right are membrane surfaces after fouling. In this image, you can see colloidal fouling and chemical reverse osmosis membrane before and after fouling, and in the bottom image, biofouling and chemical reverse osmosis membrane on the membrane surfaces have illustrated. In this image, the different types of fouling have illustrated, and you can compare them. A. Biofouling, B. Organic fouling, C. Inorganic scaling, and D. Colloidal fouling. Fouling forming types. For the complete blocking, it is assumed that each particle reaching the membrane blocks a pore without superimposing over other particles. For the standard blocking, it is assumed that particles deposit within pores and the pore volume decreases proportionally to the volume of deposited particles. For the cake filtration, it is assumed that depositing particles don't block pores either because the membrane is dense and there are no pores to block, or because the pores are already covered by other particles and therefore are not available to block. For the intermediate blocking, it is assumed that some particles deposit on other particles, as in cake filtration, while other particles block membrane pores, as in complete blocking. Fouling also can be divided into reversible and irreversible fouling based on the attachment strength of particles to the membrane surface. Reversible fouling can be removed by a strong shear force of backwashing or by lowering driving pressure on the surface. Formation of a strong matrix of fouling layer with the solute during a continuous filtration process will result in reversible fouling being transferred into an irreversible fouling layer which cannot be removed by physical cleaning. Scaling. Scaling can be described as coating on the membrane formed by inorganic precipitation or crystallization. Usually, they only occur with nanofiltration and reverse osmosis membranes if, for example, the solubility limit of dissolved salts is exceeded by excessive concentration on the membrane surface. Fouling by scaling is worse with more concentrated feed solutions, therefore the last modules in the plant are most affected because they are exposed to the most concentrated feed water. In this slide, the cells that most commonly form scale on the membrane have presented. Calcium carbonate, which can exist in the form of calcium and bicarbonate ions in industrial water, brackish water, and seawater, is the most common type of alkaline-based scalant in reverse osmosis membranes. Other types such as calcium sulfate, silica complexes, barium sulfate, strontium sulfate, calcium fluoride, and magnesium hydroxide. The principal states of scaling in reverse osmosis membrane systems are illustrated in this figure. One of the most predominant factors that governs the scale formation is the availability of nucleation sites. Upon the nucleation and formation of microcrystals that grow over time, the membrane surface is deposited with the mineral scales that damage the selective layer and deteriorate the water transport. In addition to the kinetics of crystallization and precipitation, the membrane morphology and process conditions also play very critical roles in dictating the severity of scaling. Particularly in the high-pressure membrane system, concentration polarization is known to be the main factor that contributes to the increasing cell concentration at the membrane surface, hence leading to particle deposition. This table has provided as predict table of scaling compounds. You can know your scaling potential with this free predict table of scaling compounds and the conditions that cause them to precipitate. How can you use this table? For example, if you want to know your solution has potential for calcium sulfate, you should measure the concentration of the individual ions of this compound in milligram per liter at their solubility limits. If calcium is bigger than 751 mg per liter and sulfate is bigger than 1799 mg per liter in your water, then there is calcium sulfate scaling potential. The sum of these two numbers has written on the top of the cell as solubility of compound in milligram per liter. For better understanding, let's have an exercise. A list of parameters in a reverse osmosis brine has presented in this table. Determine the compounds that have escape potential. To find these compounds, you should look at the concentration of the parameters that are out of the number in the chart. In this case, parameters such as calcium, sulfate, aluminum, and pH are out of the limits. If you look at the chart, these parameters specified in red color, then the periodic table of scaling compounds demonstrates that the reverse osmosis brine has calcium sulfate and aluminum hydroxide scaling potential. Scaling analysis. Analysis of the feed water and calculating the expected concentration factor in the brine determine the proclivity of particular feed water to produce scale. The ratio of the product water flow rate to feed water flow rate is called the recovery rate. With plants that operate below a concentration factor of 2, that is 50% recovery rate, scaling is not normally a problem. However, many brackish water reverse osmosis plants operate at recovery rates of 80 or 90%.